To begin the lecture notes for Section 3 of Chapter 6. In Section 3, we're going to look at heating systems, and that might be in your house or in a building. Most homes and public buildings contain some type of heating system. Simplest and oldest heating system, wood or coal, is burned in a stove. The heat that is produced by the burning fuel is transferred from the stove to the surrounding air by conduction. If you walk up to that stove and touch it, it's hot. Convection. Oftentimes there's a fan on the back of the stove that pushes the heat into the room. That would be via convection currents. And radiation. If you walk up to the stove, why do people stand next to fireplaces or stoves? Because the fireplace radiates that heat. When you put your hands out, you can feel that heat. That's radiation. One disadvantage of this system is that heat transfer from the room in which the stove is located to other rooms in the building can be slow. If it's just radiating out, chances are it won't get to every room in the building. Forced air systems. This is the most common type of heating system in use today, and it's a forced air system, probably the one that you have in your own home.
In this system, fuel is burned in the furnace and heats a volume of air. A fan then blows the warm air through a series of large pipes called ducts. The ducts lead to openings called vents in each room. Cool air returns to the furnace through additional vents where it is reheated.
That is a forced air system. Another type of system in some older homes, and you can also say in some newer homes, if you have what's called, I know my house has hydronic heat. There are baseboards on the floor with little baffles, and hot water flows through that system and heats up my rooms. Radiator is a closed metal container that contains hot water or steam. I know that if you live in an older house down on the river, there's a lot of those older mansions, and they may still have a radiator system. The thermal energy contained in the hot water or steam is transferred to the air surrounding the radiator by conduction. The warm air then moves through the room by convection. If you were to hold like a piece of tissue paper or something above a radiator, you may see it start moving because of the convection currents that are set up above that heat source. In radiator heating systems, fuel burned in a central furnace heats a tank of water. A system of pipes carries the hot water to radiators in the rooms of the building. After the water cools, it flows through the pipes back to the water tank and is reheated. Electric heating systems. This is probably one of the most expensive heating systems. An electric heating system has no central furnace. Instead, electrically heated coils placed in floors and in walls heat the surrounding air by conduction. Heat is then distributed through the room by convection, and it doesn't necessarily have to be a fan that's pushing the heat around. Just the fact that you have hot and cold intermix sets up those convection currents. You may have some form of electric heating. Oftentimes, if you have a room that's may not be ducted or may not have a heat source, keeping off it. If they add like a sunroom, they'll have an electric heating system, and like I said earlier, they're very expensive. Nowadays too, you might have like electrically heated coils in the floors, although a lot of the newer systems, that's actually hot water, like a radiator system in those pipes that they put in the floor. When I lived in Korea, a lot of the apartments I lived in, or if I visited my Korean friends, they would have what's called ondol heating, and their floors were warm. And the modern systems may be electric or hot water, but the old systems, they actually had little charcoal pots and like a crawl space, and then they had an opening on both ends, and that would set up a convection current to carry that heat through the house and warm up the floors. Solar heating. Radiant energy from the sun can be used to help heat homes and buildings. There are two types of systems that use the sun's energy for heating: passive solar heating system and active solar heating system. Everybody that's listening to this lecture utilizes a passive solar heating system, unless you live in a cave without any windows. In passive solar heating systems, materials inside a building absorb radiant energy from the sun during the day and heat up. At night, when the building begins to cool, the thermal energy absorbed by these materials helps keep the room warm. Right now I'm sitting in the classroom, the sun is shining in through the windows, and it's heating up this room, a passive solar heating system. An active solar heating system, active solar heating systems use solar collectors that absorb radiant energy from the sun. The solar panels that I put on the roof of the gym, that's an active solar system. Saves our school about 13% on the energy bill because we get the energy from the sun and we're able to use that. Collectors usually are installed on a roof or south side of a building. Radiant energy from the sun heats air or water in the solar collector. The black metal plate absorbs radiant energy from the sun, and the absorbed energy heats water in pipes just above the plate. A pump circulates the hot water to radiators in the rooms of the house. The cooled water then is pumped back to the collector to be reheated. This explanation is more of an example of like a solar water heater that actually has the hot water. Solar collectors don't necessarily have the hot water in them. They just have what's called a photovoltaic cell that is able to collect that energy, and then it's converted into useful electricity in our case in our school. Thermodynamics. Thermal energy, heat, and work are related, and the study of the relationship among them is thermodynamics. Heat and work increase thermal energy. You can warm your hands by placing them near a fire so that heat is added to your hands by radiation. If you rub your hands and hold them near a fire, the increase in thermal energy of your hand is even greater. Both the work you do and the heat transferred from the fire increase the thermal energy of your hands. Your hands can be considered as a system. A system is anything you can draw a boundary around. Okay? And we say that our Earth is essentially a closed system because energy comes in, but very little of it gets out. Little matter is transferred out of the system. The heat transferred to a system is the amount of heat flowing into the system that crosses the boundary. So in this example of pumping up a bicycle tower, you're putting the energy in, but the heat transferred from, and this tube will heat up. That heat transferred escapes and crosses the boundary. The work done on a system is the work done by something outside the system's boundary. According to the first law of thermodynamics, the increase in thermal energy of a system equals the work done on a system plus the heat transferred to the system. The temperature of a system can be increased by adding heat to the system, doing work on a system, or both. The increase in energy of a system equals the energy added to the system. Closed and open systems. Like I said, basically our Earth is a closed system. A system is an open system if heat flows across the boundary or if work is done across the boundary. Then energy is added to the system. If no heat flows across the boundary and there is no outside work done, then a system is a closed system. Thermal energy of a closed system doesn't change. Because energy cannot be created or destroyed, the total energy stays constant in a closed system. The second law of thermodynamics. Can heat flow spontaneously from a cold object to a warm object? This process never happens, but it wouldn't violate the first law of thermodynamics. We all know that heat flows from warm to cold, hot to cold. The flow of heat spontaneously from a cool object to a warm object never happens because it violates another law, the second law of thermodynamics. One way to state the second law of thermodynamics is that it's impossible for heat to flow from a cool object to a warmer object unless work is done. In the ice cream experiment, the half and half inside the cup and the ice cream balls, that heat is transferred out of that container into the ice. If you give a book sitting on a table a push, the book will slide and come to a stop. Friction between the book and the table converted the work you did on the book to heat. As a result, the book and the table became slightly warmer. Is it possible to do the reverse and convert heat completely into work? The second law of thermodynamics makes it impossible to build a device that converts heat completely into work. A device that converts heat into work is a heat engine. A car's engine converts chemical energy and gasoline into heat. The engine then transforms some of the thermal energy into work by rotating the car's wheels. However, only about 25% of the heat released by the burning gas is converted into work, and the rest is transferred to the engine's surroundings. So a gasoline engine isn't that efficient. The heat engine in a car is an internal combustion engine in which fuel is burned inside the engine in chambers or cylinders. Each cylinder contains a piston that moves up and down. Each up and down movement of the piston is called a stroke, and the automobile and diesel engines have 4 different strokes. This is a graphic of an internal combustion engine.
The intake valve opens as the piston moves downward, drawing a mixture of gasoline and air into the cylinder. The intake valve closes as the piston moves upward, compressing the fuel-air mixture. A spark plug ignites the fuel-air mixture. As the mixture burns, hot gases expand, pushing the piston down. As the piston moves up, the exhaust valve opens and the hot gases are pushed out of the cylinder.
Friction and the efficiency of heat engines. Almost 3/4 of the heat produced in an internal combustion engine is not converted into useful work. Even if friction were totally eliminated, a heat engine still could not convert heat completely into work and be 100% efficient. A refrigerator does work as it moves heat from inside the refrigerator to the warmer room. And if you've ever stood near a refrigerator on the outside of it, you'll feel that either on the back or wherever there's like a fan, you'll feel that it's actually warm on the outside. A refrigerator contains a coolant that's pumped through pipes on the inside and outside of the refrigerator. Liquid coolant is pumped through an expansion valve and changes into a gas. The gas then is pumped to a compressor that does work by compressing the gas. Because the gas is warmer than the room, thermal energy flows from the gas to the room. As the gas gives off heat, it cools and changes to a liquid. So in this graphic, for example, the heat from inside the refrigerator is transferred to the cooling coils. All right, those cooling coils circulate, constantly keep it cooling so that the heat from like the food and the contents of the refrigerator is transferred into those heating coils, and then it's either pushed or allowed to flow into the room. And these cooling coils, they heat up, they go through a compressor, which when you compress a gas, it gets colder, makes it colder again, and keeps that cycle going. Liquid coolant then is changed back to a gas and a cycle is repeated. An air conditioner operates much like a refrigerator, except that warm air from the room is forced to pass over tubes containing the coolant. The warm air is cooled and then forced back into the room. If you've ever stood on the outside of an air conditioner, you'll notice that it's probably warmer than the front side of an air conditioner. Thermal energy that is absorbed by the coolant is transferred to the air outdoors. A heat pump is a two-way heat mover. Some of you may have these in your house, that it'll air condition in the summer, and in the winter your parents or somebody flips a switch and it acts as a heater in the winter. In warm weather it operates as an air conditioner, as I just said, and in cold weather a heat pump operates like an air conditioner in reverse. The coolant gas is cooled and is pumped through pipes outside the house. There, the coolant air absorbs heat from the outside air, and the coolant is then compressed and pumped back into the house where it releases its heat. The human body, your body uses evaporation to keep its internal temperature constant. When a liquid changes to a gas, energy is absorbed from the liquid's surroundings. As you exercise, your body generates sweat from tiny glands within your skin. As the sweat evaporates, it carries away heat. Many energy transformations occur around you that convert one form of energy into a more useful form. However, usually when these energy transformations occur, some heat is produced. This will conclude the lectures for Chapter 6, especially Section 3. We'll go over the questions, and don't forget to do the accompanying review section for Section 3, the questions. They'll be posted on My Big Campus. Complete them and submit. Question 1. The study of the relationship among thermal energy, heat, and work is thermodynamics, letter D. Question 2. According to blank, the increase in thermal energy of a system equals the work done on a system plus the heat transferred to the system. This would be the first law of thermodynamics. Doing work on a system is a way of adding energy to a system. Question 3. How does a refrigerator work? Refrigerator coolant absorbs thermal energy from inside the refrigerator. The heat of the food or the contents of the refrigerator moves towards the coolant in the cooling tubes and releases it into the surrounding air. That will conclude the lecture for Chapter